back to the last part of this long lecture. Now, static stability is so cool. Sometimes I wish I could teach a whole course about static stability, although I have no idea who would take such a thing. Meteorologists get so excited about static stability. If you like hanging out and watching the Weather Channel or something like that, you know that stability is part of the story about things like how we get thunderstorms. I mean, if we're going to get a thunderstorm where we're lifting air from the surface of the Earth all the way to the tropopause, we need to not have the atmosphere fighting us on this. We want the atmosphere to encourage the growth, the rising motion there. We need layers of the atmosphere that are statically unstable, or at least not all that stable. That's a whole nother battle for a different day as to how we get that, okay? But there are lots of other applications for static stability in the Earth's atmosphere, including ones that are near and dear to folks who want to go into wind power. Static stability is in control of a lot of what's going on in the boundary layer, and in particular with regard to the wind profile. Now, in later lectures, we're actually going to pick apart different wind profiles that we can make assumptions about, like the log wind profile and so on. But we're not doing that today. Rather, I just want to kind of make like a slice through the boundary layer here and kind of get a feel as to why stability is going to matter. Let's say it's statically stable down here in the boundary layer here. Now, down near the surface of the Earth, it's not terribly hard to see why those arrows get small there. Well, my winds are not all that strong. I mean, these are the air parcels that are being dragged through trees and buildings and billboards, and, you know, there's a lot of obstacles to the flow. And it's not terribly hard to see how the winds above that are not touching flagpoles, power lines, buildings, etc., are not slowing down at all. If the atmosphere, if the boundary layer is statically stable, it's really hard to take the air parcels that are down near the surface with so little momentum and bring them up higher in the atmosphere to slow down those winds in the boundary layer. And under those same stable conditions, those higher momentum air parcels that are up high in the atmosphere are really hard to bring down to the surface. They all want to stay at their own altitude. So under statically stable conditions, we're going to see a certain kind of wind profile where the winds are going to be really weak, really weak at the surface, but once you get away from the surface, the winds will actually be fairly strong. That is in contrast to what's going to happen if the boundary layer is statically unstable, where we're going to be producing all kinds of rising and sinking motions, all kinds of rolling motions and so on, that are continuously working to mix this layer of the atmosphere. Now, wind speed is not exactly a conserved quantity, but we certainly have some sense that there's like momentum involved and so on. If we take air parcels from near the top of the boundary layer that have a lot of wind velocity, a lot of momentum, and we mix them downward towards the surface, we're increasing the wind speeds down low, and I made the arrows down low longer. And if we take wind speeds, air parcels from down near the surface where the wind speeds are lower, and we can lift them up with updrafts up to higher levels of the boundary layer, and then mix them in with the faster air around them, well, we actually kind of have made a way where the wind speeds are stronger down near the surface and weaker, the winds are stronger than you originally would have expected down near the surface, and the winds aren't as strong as you would have expected aloft. And the only difference between these two conditions here was the static stability of these layers. This is going to have everything to do with the wind profile that you're able to observe. And again, that's what the next couple of lectures are going to be about, is how static stability ends up telling us important things about what kind of profile to expect of the winds at the kind of levels where like wind turbines are and so on. So changes in wind and static stability are hugely important in regard to like modifying the wind profile. So I guess we need to understand how you can make changes to a layer's static stability. Well, let's turn back to this slide here where I've got a layer defined between those two yellow lines there, and I'm going to say that, well, if we can remember that the static stability of this layer can be determined by, let's just say, the environmental lapse rate, okay? Well, strictly speaking, no. We're comparing the environmental lapse rate to the dry adiabatic lapse rate. That's what determines the stability, but the dry adiabatic lapse rate's a constant. That's not exactly rocket science there. So it's really only the environmental lapse rate that we can do anything to change. Well, I gave you over there on the left how we figure out the environmental lapse rate gamma of this layer, and I copy and pasted over here our three rules about how we use gamma and gamma d to figure out the static stability of the layer. Is it statically stable, statically unstable, or statically neutral? Well, I invite you to kind of pick through that a little bit and think, okay, if the gamma d is constant, for big values of gamma, this is what happens. For little values of gamma, this is what happens. Oh, I see. From the above rules, it becomes clear that the layer becomes less stable as the ELR increases and more stable as the ELR decreases. Bigger numbers of the ELR mean that layer is less and less stable, and smaller numbers, including negative numbers of the ELR, mean that the layer is less stable, is more stable rather. So if I just sort of zoom in on that equation there and start thinking about this, I've got this equation for my environmental lab straight gamma, and what would I have to do to this equation to make this number bigger? Okay, well, I only can mess with the numerator, because the denominator, that's just the height of the top and the bottom of the layer. I'm not in control of that. So I guess I want to change the difference between top and bottom, the temperatures of the top and the bottom. In particular, I want that number to be bigger if I want this layer to be less stable. In other words, if I want to increase my environmental lapse rate. Okay, well, that means I either need to cool the top, or I need to heat the bottom, or some combination of both. That would increase the difference between the temperature at the top and the bottom of the layer, which would make the layer less stable. Okay. Again, I would invite you to work your way through on a piece of scratch paper the math just to prove to yourself that that's got to be right. But since the temperature of the top is generally going to be less than the temperature of the bottom, you can work your way through this and see, oh yeah, that does make the ELR bigger. That's great. Alright, so we either got to cool the top of the layer or we've got to warm the bottom of the layer. Well, alright, let's think of a layer in mind. How about the surface? Let's think about the layer of the lowest, few tens of meters, 50 meters or something like that. The lowest surface layer of the atmosphere. For the layer at the surface, your best bet to change the stability of that layer is to warm the layer from the bottom. To increase the temperature of the bottom by having a flux of heat from the surface into the lower atmosphere. Now I've defined a little rectangle there. I've tried to make it look like it's sitting there on the surface of the Earth right there. We could have a flux of heat. Oh, flux. We didn't have that word since like the first module of the course, I don't think. Flux, remember, stuff transporting through a unit area per unit time. So in this case, we're talking about a flux of heat. So joules of heat passing through a square meter of the surface per unit time. In this case, it's probably mostly through processes like conduction, where like when the ground is hotter and the air is colder, the layers touching each other, the air touching the ground transfers heat from the ground into the atmosphere. There's a flux of heat by conduction. Okay. Well, let's see here. The flux of heat through that square meter of the surface of the Earth. We're going to give that a name, the heat flux, and we'll use the symbol big H. And big H is going to be defined so that it's positive when the ground is warmer than the atmosphere, and so the ground is transferring heat up out of the ground into the atmosphere. It'll be negative if the ground is colder than the atmosphere. This symbol H is not a standard symbol for this term, but we won't go there because the actual symbols are complicated and there's a long story behind them and so on. H is just fine. Near the surface of the Earth then, in many ways, this H is the story of stability. It's not going to be necessarily the story of stability with regard to like a thunderstorm and a giant updraft that reaches all the way to the tropopause, but for like how stable is the lowest few tens of meters near the surface of the Earth or something like that, H is kind of the story. If H is greater than 0, it means that the air is colder than the ground. So heat is going from the ground into the atmosphere, warming the bottom, kind of cooking the atmosphere from the bottom. But that makes the atmosphere statically unstable, right? Now there's warm air near the bottom when those air parcels are likely to rise, all that kind of good stuff. By warming the atmosphere from below, we have made the atmosphere statically unstable. I'll skip down to H is negative. If H is negative, well, that means that the atmosphere is warmer than the ground. The cold ground touches like maybe at night or something like that. The cold ground is touching the warm air and heat is being extracted by conduction from the warm air into the ground. That's a negative heat flux. We're cooling the bottom of the layer, making it less and less likely that these air parcels are going to be able to rise because they're colder than the air around them. If we try to lift them, they're going to be colder. They're just going to sink back down to the surface. And of course, H being equal to 0 is the statically neutral situation. Again, this is really only a trick that's going to be working for down in the boundary layer, but that's where your wind turbines anyway are, so let's just not stress that. That's pretty cool. this nifty relationship between the flux of heat at the surface of the Earth and the stability and the production of rising and sinking motions and mixing, and it's all going to be tied to how this stuff works together to create the wind profiles that we observe. This is going to have everything to do with the wind profile. It's going to have to do with how the wind profile changes over the course of the day. It's going to be about how the wind profile changes over the course of different weather conditions and so on, all of which is fundamental to the amount of wind that a wind turbine is able to harvest energy from. All right, this is going to be a cool module. All right, before we move on, we are done with this lecture, but let's do three quick questions. Question 1. A layer of the atmosphere gets more stable if the ELR for that layer increases, decreases, does not change, or the static stability is not related to the ELR. Which of these is what happens if the layer gets more stable? Make a choice from those 4 options and get some feedback before we move on to question 12.